Welcome to today's Explainer. Let's just dive right into it. Today, we're putting together an exclusive exam playbook, looking at the absolute core computer science concepts of programming languages, translators, and IDEs. But look, we aren't just memorizing textbook definitions today. We're looking at this strictly through the lens of maximizing your marks. By analyzing official examiner reports and mark schemes, we're going to build a cheat sheet designed to help you avoid the most common pitfalls and secure literally every single point on the table. All right, to get our heads in the game, check out this real past paper question. Describe what is meant by a low-level language. Seems pretty simple, right? It's just a 2-mark question. But you would be shocked at how many candidates either leave these marks totally blank or write something that just barely misses the official rubric. Mentally lock in your answer right now, and let's see how it actually holds up as we go through today's explainer. So here's our game plan for today. We've got high-level versus low-level languages, the translator trio, compilers versus interpreters, maximizing those IDE marks, and finally, some top examiner secrets.
Let's kick things off with Section 1, high-level versus low-level. We're tackling the absolute highest frequency error right out of the gate. There's a direct quote from the Principal Examiner report saying candidates often confuse the benefits. They interpret that high-level means more difficult. This is a massive, massive red pen trap. Because the word high is in the name, candidates kind of panic. They assume it means advanced or super complicated or harder to debug. But the reality? It's exactly the opposite. Let's clear this up so you never throw away these easy marks again. Straight from the official mark scheme, high-level languages are problem-oriented and written in English-like statements. Because of that, they're way easier to read, write, and debug. Plus, they're machine-independent, meaning you can easily port them across different hardware. On the flip side, low-level languages relate directly to the hardware's architecture. They use mnemonics, like LDA for load, and they are highly machine-dependent. The huge benefit here is that a low-level language allows for direct manipulation of the bare metal computer hardware. So, your crucial takeaway? High-level means closer to human English, and low-level means closer to computer hardware.
Moving right along to Section 2, the translator trio. Okay, since a computer basically only understands raw machine code, we absolutely need software to bridge the gap. But listen closely to this master tutor tip. Examiners are totally exhausted seeing candidates lose marks because they describe the benefits of translators when the question is specifically asking for their operation. If the exam asks how a compiler works, do not just write, "it runs fast." You need to actually describe the technical mechanics of what it does. To nail this, you absolutely need to memorize this translator trio matrix. Look at the inputs first. Both compilers and interpreters take high-level language as their input. An assembler is the only one that takes a low-level language, specifically assembly language. Now check out the output row. Both compilers and assemblers pump out a standalone executable file. An interpreter does not produce an executable file. Keeping this simple matrix locked in your head will completely save you if a tricky multiple-choice or matching question pops up on your paper. Which brings us to Section 3, compilers versus interpreters. We're zooming in on honestly the most heavily tested face-off in the entire software syllabus. Let's walk through the chronological operation of a compiler. Step 1, a compiler translates the entire code all at once, completely finishing the translation before any execution even starts. Step 2, if it hits any mistakes, it spits out a full error report displaying all the errors in the code, which, let's be real, we have all stared at in sheer despair at least once. Step 3, once you fix every single error, it creates an independent executable file. Just remember, that executable file will never be created until the code is 100% error-free. Now, let's contrast that directly with an interpreter. Step 1, an interpreter translates and executes the code line by line. It reads a line, translates it, and just immediately acts on it. Step 2, because it's running live, it stops execution the exact moment an error is found. Boom, hard stop. Step 3, it only continues execution once you correct that specific error. And remember from earlier, it never produces an executable file, meaning you will always need the interpreter software installed on the machine to run the program. Let's pivot to Section 4, maximizing your IDE marks. So we've written our code and translated it, but where are we actually doing all this work? Here is the exact mark scheme-approved definition you need to memorize. An IDE, or Integrated Development Environment, is a suite of programs and tools providing a unified platform. The magic phrase you need to remember here is without switching software.
Instead of writing in a text editor, saving it, opening a separate compiler, and then launching a separate debugger, the IDE brilliantly bundles the whole shebang into one seamless interface.
And here is your ultimate cheat code for IDE exam questions. Examiners constantly note that when asked for IDE features, students just list buzzwords like debugger or pretty print and miss out on half the marks. The secret? Always pair the function with its specific role. If it's a 2-mark question per feature, you get 1 mark for naming the tool and the 2nd mark for clearly describing what it actually does.
Let's rapid-fire the most common IDE functions alongside their exact roles straight from the grading rubric. First up, the code editor. Its role is literally to let you write and edit program code. Second, the debugger. Its role is to allow you to single-step through your code or set breakpoints to examine variables. Third, error diagnostics. Its role is to alert you to errors and suggest fixes while you're actively typing. And finally, pretty print. Its role is to automatically color code and indent the code to improve readability. Memorize these pairs, and you're going to lock down maximum marks.
And finally, we hit Section 5, Top Examiner's Secrets.
We're in the final stretch of our playbook, and I need you to burn this hard and fast rule into your brain. No marks are rewarded for using brand names of software packages or hardware. This is an absolute tragedy of a trap. If a question asks for an example of an operating system and you proudly write Windows, you get 0 marks. If it asks for spreadsheet software and you write Excel, 0 marks. You have to use generic technical terms. Say operating system, not Windows. Say web browser, not Chrome. Please, do not let a brand name rob you of a point you clearly understand.
Okay, here is the perfect textbook answer to a classic, highly tested exam question. Why on earth does a programmer use an interpreter during development, but a compiler for the final release? Well, during the development stage, the programmer uses an interpreter because its line-by-line execution makes it incredibly easy to find and debug errors as they happen. But for the final release, they switch to a compiler. Why? Because the compiler translates the whole code at once to produce a fast, standalone executable file that the end user can just click and run without needing the source code or any translation software.
So, as we wrap up today's explainer, I've got to ask you, how many easy marks have you been leaving on the table simply by confusing operation with benefits, or by forgetting to pair an IDE function with its role? More importantly, which of these exact plays are you going to use first on your next paper? The knowledge is officially right here in the playbook. Now it's just time for you to go out there and execute. Thanks so much for joining me, and happy studying.